66 million years ago, a rock fell from the sky. Within a few hours, the world as it had existed simply stopped existing. 3/4 of everything alive on the planet vanished. Everyone knows that part, but almost nobody knows what happened the next morning. A year later, 1,000 years later, 1,000,000. This isn't a story about an ending. This is a story about what came after. How did life even manage to recover after 3/4 of everything alive on the planet was wiped out? Who exactly survived those first horrific years? And what gave them that chance? How long did it take before the first large animals reappeared after the catastrophe? And how did small, unremarkable mammals hiding under the feet of dinosaurs turn into the rulers of an entirely new world? Let's start with the impact itself. Quickly, we've already covered that in detail in another video. And then we'll go straight to the part almost nobody looks at. 66 million years ago, an asteroid roughly 10 kilometers across entered Earth's atmosphere and slammed into what's now the Yucatan Peninsula in Mexico. The Chicxulub crater. The energy of the impact, equivalent to 100 teratons of TNT. Billions of times more powerful than any nuclear weapon humanity has ever built. The dinosaurs, apart from birds, vanished. Marine reptiles vanished. Flying reptiles vanished. 3/4 of every species on Earth vanished. We've told that story already. Now, here's what actually matters. What happened in those first hours, days, months? Because that's where it was decided who got the chance to keep living. The newest research, published just this past summer of 2026, by a team led by planetary scientist Brendan Johnson at Purdue University, paints a far more detailed and far more terrifying picture of those first moments than we used to think. When the asteroid struck Earth, it blasted an enormous amount of molten and vaporized rock straight out into space. That material rose above the atmosphere, and then it started falling back down. Billions of white-hot glass and rock droplets, called spherules, came screaming back through the atmosphere at cosmic speed. The friction of those particles against the air as they fell generated an intense pulse of heat. And a thin, extremely fine layer of dust that had already filled the upper atmosphere acted like a blanket. It trapped that heat, radiated it back down toward the surface, boosting the surface heating by roughly 3.5 times what scientists used to estimate. The result, in Johnson's own words, was that we're in a regime where you could literally kill everything within the first hour or two. Stop on that line for a second. That's not a metaphor. That's a direct quote from a scientist who just ran the numbers. Not a lot of things died. Everything. Within an hour or two. That's the world this story actually starts in. At first, the sky went dark. The sun blotted out by debris thrown up from the impact. Then, as the spherules began entering the atmosphere, a red glow appeared overhead. And very soon after that, researchers say the eyes and skin of any exposed animal would have started to burn. Wildfires ignited almost simultaneously across the entire planet. At least everywhere, the heat pulse crossed a critical threshold. Forests, scrubland, grass, anything that could burn, burned. Any animal caught out in the open, without a burrow, a cave, or a body of water deep enough to protect it, was doomed. Quite literally, within that first hour or two. In the immediate vicinity of the crater, everything alive died almost instantly, regardless of whatever came after. The shockwave. Tsunamis hundreds of meters high, rolling across the Gulf of Mexico and the Caribbean. Earthquakes stronger than anything ever recorded in the history of seismology. Traces of seismically triggered waves have been found as far as 3,000 kilometers from the crater, including the famous mass death site in North Dakota that scientists named Tanis, where fish and other animals were found buried alive within minutes of the impact. But the real question at the heart of our story isn't about the ones who died instantly, in the first seconds or minutes. It's about the ones who survived those first horrific hours, who hid deep enough, far enough, fast enough to escape the heat pulse and the global fires. Those are the ones who made it through the sharpest, most violent edge of the catastrophe, who then walked straight into the next, much longer phase of the ordeal. The fires and the heat pulse were over within hours, maybe a few days at most. But they left something behind that was far longer lasting and far more lethal. Studies of organic material recovered from inside the Chicxulub crater itself show that somewhere between 750 trillion and 2.5 quadrillion grams of black carbon, soot, entered the atmosphere and spread across the entire planet within hours of the impact. That soot, combined with sulfate aerosols and the finest dust thrown up by the blast, triggered what scientists call an impact winter. The sun disappeared. Not figuratively, literally. A thick layer of soot and dust in the upper atmosphere blocked the vast majority of sunlight from ever reaching the ground. Depending on the estimate, that lasted anywhere from several months to several years. Without sunlight, photosynthesis stopped. Not just on land. In the ocean, too. Phytoplankton, the base of almost every marine food chain on the planet, began dying off in massive numbers. Global surface temperature plunged. Research points to global cooling, both on land and in the ocean, lasting at least several years after the impact. Add it all up, and the plants that had somehow survived the initial fires couldn't grow without light. The plant-eating animals that had survived the heat pulse had nothing left to eat, and the predators that had survived were left with no prey at all. On top of all that came acid rain, triggered by chemical reactions in the superheated atmosphere that produced nitric acid, and possibly sulfuric acid too, from vaporized sulfate-rich rock right at the impact site. That rain poisoned surface water, killed off vegetation that had somehow made it through the fires, and tore apart the fragile ecosystems that were trying to claw their way back. The ozone layer weakened so badly that ultraviolet radiation from space began reaching the surface in doses dangerous to most living cells. Picture this from the point of view of an animal that somehow survived those first few hours. You hid in a burrow, or underwater, or underground, and you made it through the fires and the heat pulse alive. You crawl back out, and you're looking at a world that no longer has anything in common with the one you knew before the catastrophe. The sky, dark even at midday. The air, cold, far colder than it should be. The ground, covered in ash. Dead trees, dead grass. Not a single sign of movement where life used to churn constantly. There's nothing to eat. Plants can't grow without sunlight. The plant eaters that survived are starving to death, one after another. And with them, the predators that used to hunt them. This wasn't one catastrophe. It was a chain of catastrophes, stacked one on top of another. The heat pulse, the fires, the impact winter, the acid rain. A collapse of the food chain that could stretch on for years. And in that world, survival stopped being about strength, size, or even speed. The largest, most powerful predators of the Mesozoic, the tyrannosaurs, the largest herbivores, the sauropods. Every one of them needed enormous amounts of food just to keep existing at all. In a world where almost no food was left, size stopped being an advantage. It became a death sentence. Survival now depended on a completely different set of qualities, and that's exactly where the next part of our story picks up. We left the world in darkness. No sun, no food. A food chain collapsing layer by layer. Now, the central question of this part of the story. Who actually made it through that nightmare? And what exactly gave them the chance? If there's one single principle that explains survival better than any other, it's size. The research shows an extraordinarily clean pattern. Animals over roughly 25 kilograms almost universally disappeared. Practically no exceptions. Smaller animals needed far fewer calories. They could scrape by on the meager, low-quality resources still available in a poisoned, sunless world. Think about that against the backdrop of Mesozoic giants. A tyrannosaur weighed up to 8 tons and needed tens of kilograms of meat every single day. The largest sauropods weighed up to 80 tons. In a world where plants weren't growing back for years, no animal that size stood any chance at all. The earliest mammals of this period were roughly the size of mice or shrews. Tiny bodies that needed almost nothing to survive on. They could squeeze into cracks, burrows, under tree bark. Places larger animals simply couldn't fit. Size wasn't the only factor. The second critical piece of survival was the ability to hide from the worst of it. Digging burrows turned out to be one of the most powerful survival mechanisms there was. Mammals, amphibians, some reptiles that could dig themselves underground were shielded from the direct heat pulse in the first wave of fires. Underground, the temperature stays far more stable. Protection from ultraviolet radiation, protection from direct contact with poisoned air. Water and semi-aquatic environments offered serious protection too. Water absorbs heat far more slowly than air does, giving a thermal buffer through those first, hottest hours. Crocodile-like animals, turtles, amphibians. Most of them survived largely because of this semi-aquatic way of life. And here's a detail that shatters the tidy picture of the small body rule. In 2025, scientists described a new species of Nodosuchian, an extinct group of crocodile relatives found in early Paleocene deposits in Patagonia. This animal weighed somewhere between 332 and 443 kilograms, 17 times heavier than that supposed 25-kilogram death line. And it survived the catastrophe anyway. Stop on that number for a second, because it wrecks everything we just told you. We just laid out a rule that sounded airtight, under 25 kilograms, or you're gone. And then here's an animal nearly half a ton, walking straight through that rule like it wasn't even there. So how? Freshwater ecosystems, unlike dry land and the open ocean, turned out to be far more resilient to the catastrophe. Rivers and lakes kept receiving nutrients from debris washing in off the banks, even as photosynthesis on the surface had nearly ground to a halt. An entire food web, built not on living plants but on dead organic matter, detritus, kept functioning even in total darkness. This is the third, and maybe the most important, rule of survival. In a world without photosynthesis, living plants couldn't feed living ecosystems anymore. But dead organic matter, fallen leaves, rotting roots, the corpses of animals killed by the fires, hadn't gone anywhere. It was just lying there, decomposing. And that's where detritivores step onto the stage. Animals that feed on dead organic matter instead of living plants or living prey. Earthworms, insects, small scavengers. Researchers even found direct fossil evidence of this mechanism. Fossilized burrows with characteristics that best match modern earthworms, dated to exactly the period right after the catastrophe. These burrowing, detritus-feeding worms fit perfectly with models predicting that this exact lifestyle is what let animals survive the boundary between the Cretaceous and the Paleogene. And here's what matters most. These worms, and other detritivores like them, weren't just surviving on their own. They were holding up entire food chains above them. Predators that fed on worms, insects, small scavengers had a stable food source even while the rest of the world was starving. Researchers point out directly that some predatory vertebrates that later went through an explosive evolutionary radiation after the catastrophe may owe their success to thriving populations of earthworms. The world that pulled through wasn't a world of heroic giants. It was a world of small, unnoticed scavengers and whoever was hunting them. Crocodile-like animals deserve their own moment here. The largest air-breathing animals that survived the catastrophe were the crocodilomorphs. Their secret was a semi-aquatic lifestyle and access to detritus as a food source. Modern crocodiles can survive for months without eating, living off carrion when they need to. Their young grow slowly, feeding mostly on invertebrates and dead organic matter in their first years of life. Scientists directly link these exact traits to how crocodile-like animals survived the Cretaceous-Paleogene boundary. Turtles, lizards, snakes, amphibians also got protection, often thanks to a watery or semi-aquatic lifestyle, low metabolic needs, and a high tolerance for prolonged starvation. Researchers have even identified one more hidden survival mechanism: torpor, a state of dramatically reduced physiological activity, similar to hibernation, but often shorter and deeper. Early mammals capable of entering torpor could ride out long stretches of cold and darkness just by slowing down every process in their bodies and conserving every bit of energy. Amphibians could burrow into mud and simply stay still until conditions improved. So what about the dinosaurs? Technically, not all of them vanished. Birds are avian dinosaurs, a direct branch of theropods that survived the catastrophe when every one of their non-avian relatives died out. And among birds, the exact same rule applied. Small size, a flexible diet, the ability to hide. Research shows that small body size, beaks adapted for eating seeds, the ability to fly, and the use of shelter helped certain bird groups squeeze through this bottleneck in the food web. Seeds turned out to be a critically important food source. Unlike leaves or fruit, which vanished along with the living plants that made them, seeds could sit dormant in the soil for years, waiting for the right moment to sprout, serving as a stable source of calories for any bird that could find and crack one open. And finally, the plants themselves. Because without their recovery, no animal ecosystem could ever fully come back. One of the clearest, most unmistakable signals in the geological record right after the catastrophe is what's called the fern spike. In rock layers directly above the Cretaceous-Paleogene boundary, there's a massive concentration of fern spores, far higher than anything found before or after that window. Why ferns specifically? These plants reproduce through spores instead of seeds, and they're able to colonize scorched, open, disturbed land astonishingly fast. The fern spike is direct evidence of massive forest destruction, followed immediately by pioneer vegetation moving in to reclaim the ground. At one of the best-studied sites, the Denver Basin in Colorado, this fern spike lasted roughly 1,000 years. By some estimates, no more than 71,000 years at the outside. Geologically, that's almost instantaneous. The first Paleocene mammals show up in the fossil record roughly 185,000 years after the boundary. By some estimates, no later than 570,000 years after. Seed banks buried in the soil, surviving root systems, pockets of shoreline vegetation that made it through, fungi, detritus, insects. All of these were holding up tiny surviving populations at the same time, while forests slowly rebuilt themselves from scratch. Here's a detail worth underlining. The post-catastrophe world wasn't some empty stage, just waiting for mammals to show up and take over. Plants, decomposers, insects, reptiles, birds, fish, and mammals. All of them were recovering at the same time, tangled together, holding each other up through the whole process. So, who actually survived? The small, the omnivorous, or the ones that could live off dead matter? The ones that could hide underground or underwater? The ones that could shut themselves down and simply wait out the worst of it? The ones with access to seeds, detritus, or carrion instead of living plants or large prey? None of the survivors were heroes. None of them were the strongest or the fastest by Mesozoic standards. Every single one just happened to be unremarkable enough, flexible enough, and undemanding enough to squeeze through the narrowest bottleneck in the history of life on Earth. And there they were, tiny, skittish, hiding in the shadow of what was left of the old world, standing right at the edge of something extraordinary, an empty planet. Millions of square kilometers of open space, with no large predator left, no giant left that could eat them or push them out. The question was no longer, how do we survive this nightmare? The question had become, what do we do with an entire world that just opened up? The answer to that question is exactly where the next part of our story picks up. The darkness passed. The impact winter ended. Ferns blanketed the scorched landscape. And now, the survivors faced something entirely new in the history of life on Earth. A planet almost completely empty of large animals. Millions of square kilometers of open space. And practically no competition at all. This is the story of how fast and how strangely that empty world started filling back up. The most detailed record we have of those first years after the catastrophe wasn't found somewhere remote. It was found on an ordinary-looking hillside near Colorado Springs. The site is called Corral Bluffs. For more than 100 years, scientists had only scattered fragments to work with. The odd tooth, an isolated jawbone, an exceptionally rare skull once every decade or two, to try to reconstruct that first million years after the asteroid struck. But in 2016, paleontologists Tyler Lyson and Ian Miller focused their attention on exactly this spot. And they made a discovery that changed everything. Dozens, then hundreds of skulls, skeletons, teeth, all laid out in a clean chronological sequence, layer by layer. The first million years of the age of mammals, documented in more detail than anyone had ever managed before. Stop and sit with that contrast for a second. For more than a century, this picture was built one crumb at a time. A tooth here, a jaw fragment there, decades apart. And then two researchers focused on one unremarkable hillside. And within a few field seasons, a full century of scientific uncertainty just closed. And the picture they uncovered is striking for one reason above all: speed. Right after the catastrophe, every surviving mammal was tiny, mouse-sized, shrew-sized. But within just 400,000 years of the impact, practically instantaneous by geological standards, some placental mammals had already reached 50 kilograms. This wasn't the slow, gradual recovery stretched over tens of millions of years that most people imagine. It was something close to an explosion in body size the moment the opportunity opened up. The first truly large herbivorous mammals, the pantodonts, appeared within just a few million years. By the end of the Paleocene, some of them, like Barolambda, weighed over 500 kilograms. A creature more than 2.5 meters long, half a ton of mammal, the largest animal in its forest ecosystem at the time. Predators kept pace too. Among the Masonichids, a primitive group of carnivorous mammals, dog-sized forms like Ankylogon appeared. And here's what's especially interesting. From a study published in the journal Science in 2022, scientists found that in the first 10 million years after the catastrophe, mammals grew their body size far faster than they grew their brain size. They didn't get smarter first, they got bigger first. Researchers even gave this phenomenon a name: brawn before brains. Analysis of the internal structure of these early skulls showed that these mammals relied mostly on smell, while vision and other senses stayed relatively underdeveloped. Survival in those first few million years demanded strength and endurance, far more than intelligence. But the most interesting part of the Paleocene isn't the mammals. It's who exactly filled the biggest, most dangerous roles in this new empty world. Because every mammal started out so small, non-mammals got roughly a 10 million year window to evolve gigantism, practically without competition. And the groups that seized that opportunity were about as unexpected as it gets: giant snakes. In the humid tropical swamps of Colombia, less than 10 million years after the asteroid struck, there crawled the largest snake science has ever known: Titanoboa. Over 12 meters long, up to a ton in weight. Paleontologists believe it fed mostly on fish in the crowded freshwater swamps of its time. Stop and try to picture that creature next to you for a second. 12 meters. A ton. Big enough to wrap around a grown adult the way you'd wrap around a thin branch. Giant crocodile-like predators. Pristochampsis and similar land-dwelling crocodile relatives became some of the leading predators on land. Not lurking in ambush by the water, but actively hunting on land, much like the great predatory mammals that would come much later. And maybe the strangest category of all: giant flightless birds. And here, the picture turns out surprising, almost paradoxical. Gastornis, a bird standing over 2 meters tall, with a massive skull and a beak that, at first glance, makes it look like something straight out of a Mesozoic nightmare. But research shows this bird was actually mostly herbivorous. And that's where the story takes an unexpected turn. Every reconstruction of this animal screams predator. The size, the skull, that brutal-looking beak. Anyone seeing it for the first time assumes hunter. But the truth is almost the opposite. A giant, peaceful plant eater, quietly filling the one big role no mammal was yet big enough to claim. The role of the large herbivore in a world that didn't have one. In South America, meanwhile, the forest racids were developing in parallel. The legendary terror birds, genuinely predatory this time, already sitting at the top of the food chain on that continent as early as the early Paleocene. Picture this world. Small mammals were still just starting to bulk up. And meanwhile, giant snakes, land-walking crocodiles, and enormous birds were already ruling the land. Nature, handed an empty stage, tried out wildly different actors for the lead role first. And mammals were nowhere near the obvious winners of that casting call. Not yet. Remember that feeling, because it's going to come back later in this story. And maybe you've felt it yourself, somewhere in your own life. Whenever a brand new, wide-open opportunity appears, whoever grabs it first rarely turns out to be the one who keeps it. Giant snakes, land crocodiles, strange, peaceful giant birds. All of them got the lead roles first in this empty post-catastrophe world, but not one of them ended up inheriting the Earth. Mammals, the smallest, most unremarkable contestants in this entire casting call, would stay side characters for millions of years yet, before finally becoming the main story. One more detail worth underlining. This recovery didn't happen the same way everywhere on the planet. In North America and Asia, mammals reached large sizes relatively quickly. But in Europe, the story played out differently. There, gastornithids and other giant flightless birds dominated for far longer, holding on to the role of large herbivore, while mammals across the entire continent stayed under 45 kilograms. And there's something almost unfair about that, if you sit with it for a second. Same starting line, same catastrophe behind them. And yet one continent's mammals got their real shot at success far later than everywhere else, for no obvious reason at all. Different continents, different experiments, different winners of this first race for empty ecological niches. Only later, over the following millions of years, would the picture start converging toward the mammal-dominated world we'd recognize today. Researchers also noticed an interesting pattern in the shapes of mammal teeth throughout this period. While the overall diversity of jaw shapes stayed roughly the same before and after the catastrophe, the specific groups behind those shapes changed dramatically. The archaic mammal lines that had thrived alongside the dinosaurs mostly died out or declined, and more modern, more adaptable lines, the ones that would eventually lead to today's mammals, and to you, quickly took their place. The catastrophe didn't just hand mammals an opportunity. It reshaped the entire internal structure of the mammal world itself, swapping out one set of players for another, even within the group of survivors. By the end of the Paleocene, roughly 10 million years after the asteroid struck, the picture had already shifted substantially. Mammals kept growing larger, more diverse. The first representatives of groups leading directly to modern animals began appearing. For instance, the oldest known member of the Proboscidean line, the future elephants, dated to 60 million years ago in Morocco. But real, final mammalian dominance still hadn't arrived. The largest, most conspicuous animals on land were still, often, not mammals at all. Giant birds, snakes, and crocodile-like predators continued to hold onto a huge share of the most important ecological roles. The real, irreversible shift. The moment mammals finally and permanently became the largest and most diverse animals on land wouldn't come until the next epoch, more than 10 million years after the impact itself, when the planet's climate would change once more, opening the door to the warmest period the Earth had seen in 66 million years. The epoch we know as the Eocene. 10 million years had passed since the asteroid struck. Mammals had grown bigger, but they were still splitting the biggest ecological roles with giant snakes, land-walking crocodiles, and enormous flightless birds. And now the planet was about to face another sharp change. Not a catastrophe this time, a burst of heat that would finally shape the face of the modern world. 55 million years ago, right at the boundary between the Paleocene and the Eocene, one of the fastest, most intense episodes of global warming in the entire Cenozoic era took place. A massive amount of methane, a powerful greenhouse gas, entered the atmosphere over a geologically brief window of time, somewhere between 100 and 200,000 years, depending on the estimate. Exactly where that methane came from, scientists still haven't fully worked out. Maybe from seafloor deposits destabilized by earlier warming, maybe from volcanic activity, but the result is beyond dispute. Global temperature rose by roughly 6 degrees Celsius, in what is, historically speaking, no time at all. Scientists named this event the Paleocene-Eocene Thermal Maximum, PEM for short. For the ocean, this was a fresh catastrophe. Bottom-dwelling foraminifera, tiny marine organisms, went through a mass extinction of their own, losing somewhere between 30 and 50% of their species as bottom waters warmed sharply and dissolved oxygen levels crashed. But on land, and especially for mammals, That same burst of heat became the moment of the fastest, most significant transformation since the asteroid impact itself. And here's the part of this story that's most striking. Three groups of mammals that today make up a huge share of all mammal diversity on the planet showed up in the fossil record almost simultaneously, in sync, across three northern continents at once, right at the Paleocene-Eocene boundary. Artiodactyls, even-toed ungulates, the group that today includes deer, cattle, camels, pigs, and, as we're about to see, even whales. Perissodactyls, odd-toed ungulates, which include horses and rhinos. And primates, the group that would eventually give rise to humans. These three groups didn't evolve gradually over millions of years leading up to this moment. They basically exploded into the fossil record, almost simultaneously, right as the thermal maximum began. Scientists directly link this synchronized appearance to diversification and dispersal triggered by the sudden climate shift. Stop and try to picture the scale of that synchronicity for a second. Three completely different animal lineages: future deer and whales, future horses and rhinos, future monkeys and humans, all showing up in the fossil record at once, on three separate continents, at the exact same geological moment. Almost as if something hit a start button for three different lines of life simultaneously. Why did warming specifically trigger this? Probably a shift in vegetation. The warm, humid climate of the early Eocene let dense tropical and subtropical forests spread much farther north and south than ever before. New types of vegetation, new feeding opportunities, new evolutionary niches waiting to be filled. One of the most vivid illustrations of this moment is the appearance of the first horses, Eohippus, literally, dawn horse. The first well-documented member of the line that would eventually lead to the modern horse. But it looked nothing like what you're probably picturing right now. Close your eyes and picture a horse. Fast, muscular, hooves thundering across an open plain. Now forget that image completely, because the very first true horse in history was nothing like it, about the size of a small dog. Only around 30 to 50 centimeters tall at the shoulder, with soft padded feet and several separate toes instead of a single solid hoof. It lived quietly in the shade of dense forest, carefully nibbling on leaves and soft shoots, with absolutely no hint of what its distant descendant would become tens of millions of years later. In that same stretch of time, another extraordinary invention appeared: flight in a mammal. Onychonicterus, one of the earliest known bats, already had fully developed wings. Interestingly, the structure of its inner ear suggests this species probably didn't yet have the full echolocation ability modern bats rely on, even though it was already flying beautifully. And there's something genuinely strange about that, if you sit with it for a second. This animal had already mastered the hardest, most improbable part of its future toolkit: true, powered flight. While the part that sounds simpler, the ability to see through sound in total darkness, was still missing. Evolution didn't build the easy piece first and the hard piece last. It built them in whatever order actually worked, one at a time. And finally, maybe the most astonishing story of this entire period. The story of an animal that took the exact opposite step from everything we've told you in our videos about life's journey onto land. Whales decided to go back into the water. Stop and sit with that for a second, because it flips everything this whole series has been building toward. Think about the entire journey it took to get life onto dry land in the first place. Millions of years fighting gravity, fighting dehydration, fighting for a body that could stand upright without water to hold it up. And now picture an animal whose ancestors had already finished that fight. Fully four-legged, fully land-dwelling mammals. And then, deliberately, step by step, over millions of years, they undid the whole thing, lost their hind limbs, moved their nostrils to the top of their skull, walked straight back into the water their ancestors had spent 1 billion years worth of evolutionary effort trying to leave. The ancestors of whales were even-toed, land-dwelling mammals, relatives of the very same artiodactyls that had just exploded in diversity at the start of the Eocene, the earliest Archaeocides. Primitive whale ancestors show up in the fossil record right in the early Eocene, around 54 million years ago in Pakistan. Paleocene is one of the earliest members of this line. It still looked mostly like a land animal, with long legs, but it was already spending significant time in the water, as shown by oxygen isotope analysis in its bones, indicating the animal fed mostly in the shallows of rivers and semi-marine systems. Why then, specifically? Scientists link this transition to several factors happening at once. Rising sea levels during the warm climate created new coastal and brackish ecosystems, where fresh and salt water mixed. That opened up new feeding opportunities, and possibly nudged the ancestors of whales to gradually shift toward prey living specifically in these transitional waters. The real explosion in diversity among these early whales, the Archaeocetus, happened a bit later, in the Middle and Late Eocene, fueled by further global warming during the early Eocene climatic optimum. Pakicetus, Myocetus, Dorudon. A sequence of forms that gradually, step by step, lost their hind limbs, developed a tail fluke, and moved their nostrils to the top of their heads. The exact same journey lobe-finned fish once made in reverse when they slowly gained the ability to live on land. Life proved something once again here. Evolution doesn't have a fixed direction. One line can leave the water for land. Another, millions of years later, can turn around and go straight back. We've traveled from the worst hour in the history of life on this planet to a world of horses, bats, primates, and whales swimming through the sea. Time to answer the questions we started with. How did life even manage to recover after 3/4 of everything alive was wiped out? Not through one heroic leap, through millions of tiny, parallel, interconnected processes. Ferns colonizing scorched earth, worms feeding a chain of scavengers and predators, seed banks waiting decades for their moment. Plants, fungi, insects, reptiles, birds, and mammals recovering not one after another, but together, tangled up, holding each other up the whole way. Who exactly survived those first horrific years? Not the strongest, and not the biggest. The smallest, most flexible, most undemanding. The ones who could hide underground or underwater. The ones who could live off dead matter instead of living plants. The ones who could shut down entirely and simply wait out the worst of it. How long did it take for the first large animals to appear? Far less time than you'd probably guess. Within just a few million years, giant snakes, land crocodiles, enormous birds. But real large mammals, and the final, permanent rise of mammals as the rulers of the land. That took not millions, but tens of millions of years, all the way to the start of the Eocene. And how did small, unremarkable mammals become the rulers of a new world? Not right away. First, they competed with giant snakes and predatory birds for the most dangerous roles, and often lost that competition. Only 10 million years later, pushed forward by a fresh burst of global warming, did they suddenly, almost explosively, diversify into the forms we recognize today. Horses, primates, whales, bats. 66 million years ago, one rock from space ended the reign of the dinosaurs. But that wasn't the end of the story. It was the beginning of the biggest, fastest, most astonishing recovery this planet has ever seen. A world that looked dead turned out to simply be waiting. And out of that waiting, an entirely new world was born. A world that would eventually lead all the way to you.